All right, we've been talking about how elementary row operations correspond to matrices, and that to affect elementary row operation on a matrix, it corresponds to multiplication by a matrix. Now let's talk about this correspondence between elementary row operations and matrices. In fact, the matrices that correspond to elementary row operations have a very simple form. If I want to row swap in a system of linear equations, then the row swap matrix is simply the identity matrix with two rows swapped. We'll see that in a minute. Okay, if I want to do scalar multiplication, then the identity matrix with one diagonal entry not 1 will multiply the corresponding row by that non-1 diagonal entry. And the row addition, which is really row plus a multiple of another row, is the identity matrix with one off diagonal entry not 0. All right, so let's see some examples of how this works. Look at this matrix here. Now, it's not quite the identity matrix. The identity matrix would have 1s down the diagonal. But notice here that instead of the 1 being here, it's down here. And instead of this one being here, it's up here. So in fact, the second and the fourth row of the identity matrix have been swapped. All right. Now, if I multiply a matrix by this matrix on the left, then the matrix will have its second and fourth row exchanged. All right. You can try that with some matrix, or try it with a smaller matrix. Let's look at this at a simpler example. Go here and go down. Let's just do a 2 by 2. Suppose I have a matrix like this. 3, 2, 4, 7. And let's do this simple row swap. 0, 1, 1, 0. Okay. All right, now, the usual process of matrix multiplication, the first entry here is going to be 0 times 3 plus 1 times 4, which is 4. Then this row times this one gives me 0 times 1, 0 times 2 plus 1 times 7, 7. This one's going to be 1 times 3 plus 1 plus 0 times 4 is 3. And then the next one's going to be 1 times 2 plus 0 times 7, which is 2. So notice that the rows have been interchanged. And you can see that because the first row of the result is going to be this row times this matrix. This row times this matrix. And when you multiply this row times this matrix, you're basically going to select the second row. Similarly, the second row of the resulting matrix is this row times this matrix. Now, this row times this matrix basically selects the first row. Right, so this matrix exchanges these rows, and with larger matrices, the same process occurs. Right. Now, if I want to multiply row 3 by 7, all I do is I take the identity matrix and multiply one entry, the third entry in the diagonal, by 7. Now let's again do a simple example to show how this works. Suppose I start with a matrix 2, 7, 6, 2, like that. And suppose I want to multiply the second row by a 5. So that should be 1, 0, 0, 5. All right. Now, by the same token, the first row here is going to be the first row of the matrix on the left times the matrix on the right. And you can check that that will pick out the first row. Now, on the other hand, the second row is going to be the second row of the first matrix times the second matrix. And when you see how that works, that's going to pick out 5 times the second row here. So that's going to give me 30 and 10. Okay, you can go through step by step and also see that that works. Finally, we have row addition. And suppose I want to, according to this example, I want to replace the fourth row with the fourth row plus 9 times the second row. So let's look at the fourth row here in this matrix. This fourth row here in the identity matrix is in fact the fourth row of the identity matrix plus 9 times the second row. Okay. So another way of describing this is saying that if I want to carry out some row operation on a matrix, to find a matrix corresponding to that ERO, I carry out the same operation on the identity matrix. Here I want to replace the fourth row with the fourth row plus 9 times the second row, and that's what we did for the identity matrix. Replace the fourth row with fourth row plus 9 times the second row. And you can work this out. Let's try another simple example. Suppose I want to replace the second row of a 2 by 2 with the second row minus 3 times the first row. So here's my matrix. Let's just do 8 minus 2, 1, 4, like that. And suppose I want to replace the second row with the second row minus 2 times the first row. Well, the first row is unchanged. The second row has minus 2 times the first row plus 1. And you can check that, in fact, this works. And here I get the first row remains unchanged. Second row, I take minus 2 times 8 plus 1 gives me minus 15. And then here I get minus 2 times minus 2 is 4 plus 4 is 0. Right? So, if you follow this sequence of row operations, this example, we've exchanged these two rows. That corresponds to the elementary matrix of exchanging the first two rows of the identity. Then from here to here I multiplied the first row by 1/2, corresponds to multiplying the first row of the identity matrix by 1/2. And here I've subtracted 1 times the third row plus the second row, and that corresponds to this matrix here. Subtracting 1 times the third row of the identity matrix from the second row of the identity matrix. Now these also have inverses. The inverses of these elementary row operation matrices, well, if I swap two rows, then to undo that operation, I just swap the two rows again. So you can see that this elementary row operation matrix is its own inverse. In the second case, I divided the first row by 2. And to undo that, I would multiply the first row by 2. So that gives me this elementary row operation matrix. Instead of a 1/2 in the top, I had a 2 in the top. In this case, instead of subtracting the third row from the second row, I add the third row back to the second row. So this is the inverse of the previous one. Now if I multiply these three matrices together, you can check that you recover your original matrix back again. Okay, so it all works together in a nice, neat package.